We'll try and get a quiz sometime today. All right? Something that'll be somewhat challenging, but at the same time not like blow you out of the park. All right? Blow you out of the water. All right, any questions on homework? I'll entertain like maybe one or two, and that's it, if there's anything. Any issues? Graphing, exponential functions? It's all right? Not too bad? We have a couple of more things to talk about in this section. Well, actually, just one more thing to talk about. We did not discuss last time what are called exponential equations. So let's see, where did I end? 637? Yes, okay, so we're going to do 638 today. And we're going to kind of step. Did you get my email reply? Did you send me an email about? Yes. Did you get my reply? Okay, that's fine. So we're going to step away from the graphs for a little while. All right, and we're going to look at something that we really haven't ever seen before. Normally, I want you to recall solving equations. When we try and solve an equation, we have to first be given an equation, right? An equal sign has to appear there. And then we have to be asked to solve for a specific variable. So as an example, solving equations, as an example, what we would call a linear equation would be something like this, 3x minus 5 equals 10, right? And here we'd be asked to solve for x. So you'd move the 5 over, right? You'd add 5 to both sides, and you'd get 3x's 15. Then you'd divide both sides by 3, and you would get 5, right? And we would have the solution to the equation. And then we move on, and we can do other types of equations. There's quadratic equations. Something like x squared minus 2x equals 3. That's a quadratic equation. And the technique that we use to solve a quadratic equation is different than what we use for the linear equation, isn't it? Like for linear, we isolate the x. We get the x by itself, and we just move things around. For quadratic equations, we try and move everything to one side and then try factoring it. And if the factoring doesn't work, we have to use the, what's that thing called? Quadratic formula or quadratic equation, if you want to call it that. Okay, so I would move everything over. Factor. This one factors. And you get 3 and negative 1. Right? All right, and then I can keep going through the different types of equations that we should know how to solve in this class. The next one that we might look at is something like a radical equation, where you have like square root of x plus x equals 5. I'm not going to go through this one, but we did this in the very beginning of the class. And so the technique for solving a radical equation was, anyone remember? You're going to square both sides, but you first isolate that radical, right? So you get everything to one side except the radical, then you square both sides, then you go solve whatever's there, and then you have to check your answers, blah, blah, blah. So we have a way of doing radical equations. We also can do what we called rational equations, and that would be something like x over x plus 1 minus 2 over x equals 5. Anyone remember how we do that? Find your common denominator, multiply everything through by your common denominator, and then go solve that remaining equation. So all of these types of equations are things that we should, as college algebra students moving on into pre-cal, Cal 1, we should all be comfortable with these types of equations. And what I want to point out specifically here is that in all of these equations, The x was never the exponent, was it? Because last class we studied exponential functions. What made them exponential functions was the fact that the variable was up in the exponent, right? And here, all of these equations, we never have the x up in the exponent. So the question would become, what if you have an equation where the x is up in the exponent? How would you solve that? Is there a technique? We are going to start to look at it today. We're going to realize that we can do some of them, but then we're going to get stuck, and then we'll have to introduce logs, and then once we have logs, we'll be able to solve any equation that has, well, most equations that have x up in the exponent. Okay, so the final, I guess, question here is, what about this equation, which I'm going to call I'm doing it in blue because it's different, exponential equation. How about this? 3 to the x equals 9. Can you solve that? Can you tell me what x is? You know what it is, right? Just by looking, you can tell. What is it? X is going to be 2, right? If x is 2, this works, right? Just by inspection. 3 squared is 9. So we could say the answer is x equals 2, and I'll be happy about that. But we didn't use a technique, did we? I mean, other than just like visually looking. So what about something like this? 4 to the 3x plus 1 equals 5. It's not happening, right? I mean, first of all, can you think of anything we raised 4 to get 5? No, I mean, 3 squared was 9. So you get your calculator out, you can start trying, right? You can start trying and play with it. But there has to be a technique, right? There's got to be like a method to do this. And there is. There is. That's what part of the point of the end of this section and the beginning of the next section is going to be, is how do we solve things like this? One thing you could be looking at is, okay, let's say that we go back to that bacteria problem. Remember the bacteria that quadrupled every day, right? We said that that was 4 to the x, wasn't it? What if I asked you, on what day would you have 50,000 bacteria? Then what you'd be asking yourself is, when was that function 4 to the x 50,000, right? That's the question we'd be asking ourselves. And so you have to solve for x, but it's up here. Understand? Okay, so these are all questions, right? This first one was okay. These two not so easy. So let's see what we can handle right now, because there are certain ones we'll be able to handle, like this one, right? We can handle that? All right, so first I have to give you a property. This property is important. It says this, 6.39. If a to the x equals a to the y, then x must be y. Now that might seem obvious, all right? But it is actually only true because the exponential function is 1-to-1, which means it has an inverse. So the fact that that's true is what guarantees this property. So anytime you have an equation and you have the left side and right side and they have the same base, if these are going to be equal, that means whatever's in the exponent has to be equal. Now let me illustrate this property with an example. We just did this one. 3 to the x equals 9. And we all said the answer was 2, and no one disagreed with me, right? But what I'd like for you to do is try and rewrite the problem where they have the same base. So can you rewrite maybe the 9 as having a base of 3? 9 is what? I know it's 3 times 3, but we could write it as 3 squared, couldn't we? And then you can see hopefully that you have the same base, right? A. And therefore the exponents, x and 2, are like the x and y have to be the same. So from this we could say, all right, as soon as we got to that point, x must equal 2. Okay? Now that's the approach we're going to use for this section. Next section we'll have a different approach, which will be much more powerful, and we'll actually throw this away. But it's good to have it, because sometimes this is a lot easier to do than the other method. Yeah, you're going to have to know what 9 is, or how 9 can be rewritten. And let's see how quickly this becomes ugly. How about this? 4 to the 2x equals 8. Let's just make that 2x plus 1, just for fun. All right, just for fun. So I don't think anyone here is going to be able to tell me 4 to anything is 8. I mean, I know 4 times 2 is 8, but that's not what's happening here. We're raising 4 to something. So what we need to try and do is maybe write this as having the same base. Does it work the same way that this one did? I can't write the 8 as a power of 4, right? I can't. 8 is not 4 squared or 4 to the first power, right? But it's 2 cubed, right? 8 is 2 cubed. That's the only one you can think of. Okay, if this is going to be written as 2 cubed, let me just write it down. Then if you want to use the property above, right? If you want to use that property, then this side's going to have a base of 2 also. Can you rewrite 4 as what? 2 squared. Okay, now just follow me if you can here. Everyone agree what's in parentheses is 4. And that's being raised to the 2x plus 1. Yes? All right, let me make this a little bigger so we can see it. We have 2 to the 2 being raised to the 2x plus 1 equals 2 to the 3. Now what I need, again, is that I have the same base. If I have the same base, I can match up the exponents, set them equal to each other. I have a base of 2 here and a base of 2 here, but I've got this 2 and then raised, don't I? So I'm going to have to go back to my pre-algebra course where I learned properties of exponents and recall this property of exponents. If you have x or something raised to a power and you raise that to another power, what does it become? You multiply the powers. X to the n times m. Do you remember that property? I'm putting a star next to this. This is a property of exponents. If anybody wants a cheat sheet that has all the properties of exponents on it, just send me an email. I've got some we teach that in developmental math. We just give them a cheat sheet that has all the properties. Okay? Send me an email if you're interested. I think the book has in the beginning, in the R sections. I'll tell you. Chapter R is the review chapter. Yep, page 73 is where it would start. Okay, so because of that, what I'm going to do is I'm going to rewrite this, and I'm going to multiply the 2 times the 2x plus 1. Multiply those together, because the 2 here is like the n, and then the 2x plus 1 is like the m. So what is 2 times 2x plus 1? What is it? 4x plus 2. The 2 has to distribute through to each of them, right? The 2 goes to that one and to that one. And then the right side is still 2 to the third. See how that worked? See, they have the same base now? So we have the same base. Since we have the same base, we match up the exponents. So on the next line, what I would do is write, okay, well then 4x plus 2 must equal 3. And now what type of equation is this? Linear. And we just solve it the way we normally solve a linear equation. So subtract 2 from both sides and get 1. So x is equal to 1/4. That would have been difficult to just look at and get, right? It would have been difficult to just look at that and be like, Oh, yeah, 1/4, of course, right? Just wouldn't happen. Anyone have a question on the technique? Trying to get the same bases. Once the bases match, you just go across and set the tops equal to each other. Yes. I'm sorry? You do what? Just leave it as a fraction. Yep. All right, let's try one. How about 4 to the negative 2x plus 5 equals 1/16? Anybody have any ideas here? You can rewrite 16 as what? 1 over 4 squared? Do y'all agree? See, I don't know how to teach that part, like how you see that. I mean, okay, so let's start with, let's go baby steps. 1 over 4 squared, right? But we need the same base. We can't have a fraction, so you're saying rewrite that, bring it back up, and write it as a negative exponent. Yeah, perfect. That'll work. Why doesn't this work? Do y'all agree that 1 over 4 squared is 4 to the negative 2? Yep. Now, do they have the same base? Yes. So we're going to just match up their tops. Write that down on the side. That's your new equation. Solve that. You're done. That's right. So I would expect everyone to be able to solve that at this point. 7/2, and we would just leave it as a fraction. Questions? Let's do another one, since these seem to be so much fun. I get this vibe that you're enjoying this quite a bit. Am I reading it correctly? Now, there's a dot here. This dot means multiplication, right? That means multiplication. So what do you do if you multiply? If you have the same base, right, you add the exponents, but we don't have the same base, do we? What I'm referring to is, again, another property of exponents. If you have x to the n times x to the m, this is when you add the two exponents. And while I'm talking about properties, if you have division, that's when you subtract them. Just side note, two different properties there. So I cannot put these two together because they don't have the same base, do they? Now, ultimately, we want to be able to set the equation equal. So we'd like to get all the bases the same. 3. Does everyone see that all of these have a common base of 3? 9 is 3 squared. 27 is 3 cubed. Okay, so I'm going to rewrite it. 9 is 3 squared. And I'm putting in parentheses because I really want to make sure you understand that's still raised to the 2x, right? Then times 27 is 3 cubed, and I'm raising that to the x squared. And then on the other side, 3 to the negative 1, I don't need to rewrite that. We good? Yes. Question? Yeah. Yes, we're going to use the property I had before, which I'll write it down again just so we have it. That x to the n to the m is x to the n times m. So I'm about to use that one again right here and here. Okay, so I'm going to multiply 2 times 2x, which would be 4x, so it's 3 to the 4x, times 3 to the 3x squared equals 3 to the negative 1. Now, looking at this property, back up here, this thing I wrote down, we can only have a single base on the left and a single base on the right, correct? Like a on the left to a power, a on the right to a power. Right now what we have is we have a appearing twice here. I can't have that. So is there any way that maybe we can put these together now? Do they have the same base? So it's like x to the m n times x to the m. I can rewrite it as x to the n plus m. So I can take this and rewrite that as a single 3 raised to the 3x squared plus 4x, or you could say 4x plus 3x squared. Oh, doesn't matter which order I put addition in, right? Do y'all see that? Those two went together right here using this property. Yeah. Equals 3 to the negative 1. Are we okay with that? You have the same base now, right? Both sides. So you look at the exponents, and you take those two exponents, and you set them equal to each other, and I'll do that on the next page. So I'm at the point where I'm setting 4x plus 3x squared equal to what? Negative 1. What type of equation is this? Quadratic. Move everything to one side. I'm going to put it also in descending order. Oh, well, yeah. Plus 1 equals 0. Careful. Be a little careful with that. It's 3x plus 1, x plus 1. So we go back to the very beginning of class when I said you got to be able to factor quadratic trinomials. Again, it's coming up again for us. So we get two answers, negative 1/3 and negative 1. So there are actually two possible solutions for this. Questions? Yes. Good question. No, you do not. Not for exponential equations, which is what we just solved. Unfortunately, when we get to the next section, when we have to do logarithmic equations, you will have to check your answers. It is one-to-one, but there's a restriction on the domain. Remember, exponential functions went forever both directions? Yes? We're going to see the logs, the domain's going to be cut off. You'll see. Because the log is one-to-one also. Because it's the inverse of the exponential. So it has to be one-to-one. Okay, so let me give you I think that's sufficient. I think I've shown you enough for you to be able to do your homework for this. What I'd like for you to do is page 434 and 61 through 79 odds. Every single problem out of that set is solving an equation where you have to get your bases look the same. And you got to move things around and manipulate and, you know. All right. Let's proceed. Check something real quick. Okay. 6-4. I always want to take like a real big deep breath before I start logarithmic functions because for some reason students really don't like logarithms. I don't know what it is about logarithms. I think it's mostly because the notation is something you don't haven't seen, and so it just looks so foreign that you just automatically reject it, you know. So let me write something down and see if you can understand what it is I'm trying to ask you. If I write 4 to the x equals 16, right? Tell me what it is that I'm asking you to do, like in words. Find the x that when I raise 4 to that x, I get 16, right? That's what I'm trying to get you to do here. Yes? You tell me what the x needs to be that when I use that as an exponent, I get 16 on 4. It's weird. So can't do a root. Can't do a root. No. We just did this problem. The answer is 2, right? The answer is 2. This is like this, the 3 to the x is 9. But let me write it down. What I'm going to do is I'm going to use a different notation. Something that is going to tell you that's what I want you to solve, but I'm going to write it in a different way. So here's what I'm going to write. Log 4, 16. Okay, log 4, 16 means that you're going to look at the 4, that's what we call the base of the log, and you're going to try and figure out what would you raise 4 to get 16. This is purely notation. It's asking you the same question this one was asking, written a different way. So all logarithms is an alternative notation, a different way of writing something. It's a different way of asking this question. You understand? So what we could say here is that this is equal to x. The answer to this is x. Let me give you another example. If I write down 3 to the x is 15, how would that be converted into logarithm notation? Log, and we would say base 3 of 15, right? That's the way we'd write that. How do you say it? Okay, so you could say log base 3 of 15. Log base 3 of 15. What does log base 3 of 15 mean? It means 3 to what power is 15? Does anyone know 3 to what power is 15? No. No one here knows that. Okay? Does anyone know what log base 4 of 16 is? Well, 4 to what power is 16? 2. So the answer here would be 2. All right? It's just notation. We call this on the left side exponential form. We call this on the right side logarithmic form. Logarithmic form. Log base 3 of 15. Okay, let's try another one. I want you to write this. T to the 5s equals m. I would like for you to convert that into its logarithmic form. So what you have to do to be able to go into logarithmic form is you have to have something being raised to a power equals something. So the good news is you'll always start by writing log. The base will always be the base of the thing being raised over here, which in this case was what? T. That's a 5s. Yeah, that's S. I don't know how you want to. What do I put here? M goes here. And then equals over here, 5s. If I write t to the 5s equals m, to convert that into a log form, I put log base t of m equals s. So it's really just a matter of, look, what happened here? We wrote log, do that every time. The 4 is always the base, right? This 16 here comes from the other side of the equation, and then whatever the exponent was is what goes on this side. You follow that or not? So the t was my base. You could say the 5s goes to the other side, and then whatever was over here goes in the log. What's that? The base is always going to be the base. That's the good news. The other two kind of switch places. The opposite way is easier, I think. Okay, how about this? Try and trick you. 5x to the y equals z. Try and write this as a log. So the problem that we have here is that in everything I've shown you so far, you had a base to a power, right? Base to a power, base to a power. Here, I do have base to a power, but I also have a 5 out here. That 5 is not being raised to the y, is it? Get rid of the 5. How can we get rid of this 5? Divide both sides by 5 first. X to the y equals, you could write z over 5. Now you can go to log form. What would the log form be? Log base x, z over 5 equals y. Can't, because I would have had to have given you the original problem like this. I would have had to have put the 5x in parentheses. Then that would have meant the y is applied to both of these. Because I did not put parentheses, the y is only on the x, so the 5 is not included in that power. So you got to get it out of there, so you divide through. All right, so do you kind of get the idea that if we have something written as an exponential form, we can convert it into this log form? Yes? Let's go to a new note. Let's try and go the other way. How do we go from log form back to exponential form? So convert to exponential form. Start with this one. Log base 5, 25 equals y. How do I convert that to exponential form? Okay, the base will always be the same base, right? So 5 to the what? Y equals 25. Everyone understand that? Now, as long as I've been teaching this, I've always taught my students this thing. I haven't never seen it in a book, but it just makes a lot of sense to me. I call it the loop, all right? It's the first time you're hearing me say it, but I'm going to say it a lot. The loop, all right? All logarithms can be rewritten to exponential form using this thing that I call the loop. You start out with 5, you loop around to the other side of the equation, you come back to the 25. Right, so it's this little loop that we're going to create. You're going to take 5 and you're going to raise it to this power, and that will be equal to whatever's there. So let's see if you can see that from here. I write down 5, I raise that to the y, and that should be equal to the 25. Y'all see how that worked? You may at this point not need that, but trust me, it'll help you later, all right? Right here, converts to this. Let's try another one. How about log base x m squared equals 5t? So x to the 5t equals m squared. I'll use my loop. I'm taking x, I'm raising it to the 5t. So that's what I did, right? Raised it to the 5t. Then I set that equal to whatever was right there, equal to m squared. See that? Yes or no? I mean, yes? Okay. Click yes. Click yes. Remember, that whole clicker thing was to get you all to like feel comfortable saying yes or no. And I was hoping at some point you would just tell me yes or no instead of having to do a clicker. Yeah. Okay, so we have this new way of writing things, right? We have something in exponential form. You can always convert it to logarithmic form. So I want to make a point, all right? Notice that if I'm writing 3 to the x equals 5, I want to know what x is, right? And I started class by talking about the different types of equations we can solve, right? The different types of equations that we can solve. Linear, quadratic, and when we got to exponential, we said, yeah, sometimes we can, and then sometimes we can't. This one we could not do, right? But our ultimate goal would be to figure out what x is, right? Like x equals something. X is something. And the problem is, how do you get an x out of an exponent? If it's up in the exponent, how does it ever come down, right? How does it get out of there? Well, convert it to log form for me. What is this in log form? Log base 3, 5 equals x. Holy shit, look, x is by itself, right? Right? X is by itself equals this. Now, I don't know what that is, but if the whole idea is to get x eventually, right, this conversion essentially has the effect of getting x alone. And we're going to need that. Now, the question is, what's this, right? I mean, and that's why we have calculators, because our calculators can do logarithms, and we'll be able to do that, all right? But we're just not there yet, okay? Mm-hmm. Yes. Well, what I suggest you do is, like this one right here, I did not use the loop, right? Because I had to just think about what a log is. But you can check to see if your answer is correct by doing the loop here. And if you do the loop here, it better come back to this, right? So this should be 3 to the x equals 5. That's what I started with? Yes, I'm okay now. Does that make sense? If you had written log base 3x equals 5, then if you try the loop here, you have 3 to the 5 is x. Is that what we started with? 3 to the 5 is x? No. So that meant that I wrote it down wrong. Okay? Okay. So the point of this whole thing is x is alone, right? X is alone. So we are going to have a way of getting x out of an exponent. Right there. We are happy. Yeah, we don't know the answer yet. But we actually are starting to lead ourselves to a way to get x by itself. You know, whenever we were doing linear equations, we knew what to do. Move things around, divide, quadratic factor, set each factor equals 0, and that always got us x by itself. Here we didn't really have a way. Well, it has something to do with logs. We have to be able to use a logarithm to be able to get x by itself. All right. No, log is a function. Log is the name of a function. So let me put here what's going on? Sound like me the other day during our test. Okay. The logarithm. Base A. All right, I'm going to give you the definition of a logarithm, all right? If you write log with the little base A here, and you say of x, right? That's why I'd say that, log base A of x. If I say that's equal to y, this means that A to the y equals x. That's the definition of a logarithm. That's basically what I just told you, but I'm writing it down in a more general form. Look, if you start with this, right, you turn it into this. If you start here, you do the loop, you get to this, right? That's all the definition is a different way of writing the exponential. Now, we do have some restrictions here. A must be a positive number. A cannot be 1. Does this look familiar? We had the same restrictions with exponential functions, didn't we? And the reason why we say A is positive, because if I put a negative number here, negative number to a power, we didn't even deal with that with exponential functions. We said we will not mess with negative bases. So we are going to make sure that our logs are going to follow that same pattern. We also didn't want 1 here because 1 to any power is just 1. So we throw those out. But we have one additional restriction with logarithms that we did not have with exponential functions, and that's this. I'll do it in red because it's important. And x must be greater than 0. Let's talk about why that has to be true. Why is it that when I have a logarithm, whatever I put right here has to be a positive number? Why? Well, maybe this will help. Come over here. Isn't that x? Why does this have to be a positive number? Because any positive number, right, any base that I ever plug in, raised to a number, doesn't matter if it's positive or negative, has to be positive. Why? Because this is an exponential, right? Like that's basically an exponential function. Last class, we studied exponential functions, and we said one of the properties of exponential functions was this, right? If you take any number, A, and you raise it to the x. Now, I realize in the note I just have right now, it's A to the y, right? But it doesn't matter. If it's A to any number, it's going to look like this or it's going to look like this, meaning that if the number is negative that I'm plugging in, I'm going to be above the x-axis. If I'm positive, I'm going to be above the x-axis. This thing never gets to 0, does it? Never spits out 0, never goes negative. So this note is telling you that same thing. It's saying it's impossible to put a negative right here because that would be impossible to get over here. Do y'all follow that or not? Yes? Okay, so this is going to create what we will call our domain restriction. Any questions on that? All right, now I'm going to try and blow the doors off by defining a function. Right now, all I have told you is that there's this thing called a logarithm that allows you to rewrite things. That's all I've told you. Now what I'm going to do is I'm going to define a function. The log, I'm going to say log function, base A. So before this note, I told you what a logarithm base A means. And in this note, I'm going to define what's called the log function. And I'm going to call it this. F of x is a function. And it is simply log base A of x. That's it. That's the function. You give me an x, it spits out an answer. Right? You give me an x, it spits out an answer. Now we have all the restrictions. A must be positive, A can't be 1, and the new additional thing, x has to be bigger than 0. And the reason why these restrictions are here is because that's the restrictions that we have for any log. This is the log function base A. So here's a specific example of a logarithmic function. How about the function f of x equals log base 2 of x? I wonder what the graph of this looks like. So maybe what we should do is do what we did with the exponential functions. Do you remember how we graphed the exponential functions? We created a t-table. We plugged in some x's, and this gave us our f of x. And what were the x's we plugged into the log? To the exponential? -3, -2. Do not plug those in here. All right? I know. Here's the problem that we're going to run into. It's going to happen very quickly. We're going to realize we have trouble. Can you even, don't write this down. I'm write it in red because I don't want you to write it down. Can you plug -3 in for x? No, we just said x can't be negative, right? So you throw that out. That's not even possible. Can you plug in -2? No. -1? No. Can you plug in 0? No. You only can plug positive numbers in. So let's try to plug in 1. We'll try 1. All right? So what that means is I'm going to rewrite this log. I'll write it like this. F of 1 equals log base 2 of 1. Now somebody tell me what question this is asking. What is this really asking me? What's the power I raised 2 to in order to get 1? 0. Do you agree? 0. 2 to the 0 is 1. Yes, we will have one. Yes. Do y'all agree with this? Look, 2. Now, I think the answer is 0, but let's just check it with the loop. Is 2 raised to the 0 equal to 1? Yes. 2 to the 0 is 1. So the answer is what? 0. Now, let's try and plug in 2. What's f of 2? What's log base 2 of 2? 2 raised to what power is 2? 1. Check it with the loop. 2 to the 1 is 2. That checks out. So the answer here was what? 1? Okay. Yeah, I'm glad you said that. If you try 3, what's going to happen? You're not going to be able to find it. Do y'all see that? I'm going to write it down over here. I'm not going to write it in my table. What would happen if I try and do 3? What's log base 2 of 3? So 2 to what power is 3? No clue. No clue. All right? Don't know. And therefore, I should probably not try and plug in 3. I should probably plug in the things that I know are powers of 2, which would be the next natural one would be what? 4. So how about we try that? F of 4, which would be log base 2 of 4, which is 2, because 2 squared is 4. So you've got what? What do we plug in? 4, and it spit out 2. What would the next number I should plug in be? 8. Right? Not 6, because 2 to what gives you 6? I don't know. But 2 to the third power gives me 8. So I'd want to plug in 8 next, and it should spit out 3. Do you follow me? And then I should plug in 16 and get 4. I'm sorry? That's right. We're using our brains. Yep. I mean, in terms of we're thinking through this, it's not like the exponential where I was just like -3, -2, -1, 0, 1, 2, 3, and it's just like that's what you do all the time. Here you actually have to be careful what you plug in. If this was the log base 3 function, right, instead, I could plug 1 in, but I would not want to plug in 2. I'd want to plug in what? 3, then the next one, 9, then the next one, 27, do you see? So the base is going to dictate how I create this table. Now, there's something we have not tried plugging in, which I would like for you to consider. It has to be a positive number. We've avoided fractions. We've avoided things that are smaller than 1. How about 1/2? Can I plug in 1/2? So log base 2 of 1/2. It would be -1. We have to realize that 1/2, right? Let's try our loop here. Let's just write this down. It's been proposed that the answer should be -1. 2 to the -1 is 1/2. Do we agree with this? Yes. 2 to the -1 means you drop the 2 down, right? So it becomes a 1/2. 1/2 is 1/2. That was clever. So -1. What else could I plug in? 1/4. 1/4 would spit out what? -2. Very good. Are you catching on? What would the next one I could plug in be? 1/8. And what would it spit out? -3. Okay, and then I could keep going. Y'all okay with this? Now, here comes the big moment. All right? I'm going to go back to last class. I'm going to go back to the good old folding rectangle problem. Remember this problem? We came up with 2 to the x. Then we kept talking. I was talking about Fight Club. Then we did the problem with the bacteria. Then we did cutting the paper in half. And then eventually, here it was, 2 to the x, right? And I had you plug in some values. And then I had you plug in some negative values. I want you to tell me what you see. There's something we just did in this. Do y'all see the difference? Do y'all see the similarities? It's backwards. It's the opposite. It's the inverse. Look, 0, 1 in our table right now was 1, 0, right? So in our table, the x here is the y there, and the y here is the x here on ours. And that follows for every one of these. You mean to tell me the x's and y's switch places? Right? How is it that you find the inverse of a function algebraically? You set x equal to y. You switch the x and y, right? What I'm trying to show you is that this log base 2 function is exactly the function that undoes the 2 to the x function, which means it's its inverse. Right? It's the inverse of 2 to the x. Maybe that wasn't like the wow, eureka moment I was hoping for, but okay. Yeah, thank you. Thank you. Whoa. Whoa, let's go get drinks. All right. So this is a pretty big deal, all right? What we've discovered is that if we define the function to be log base 2 of x, that it has a unique property that it will be the inverse of 2 to the x. So they should undo each other. So we notice that f of x equals log base 2 of x appears to be the inverse of what? Of 2 to the x. So I can't write it as 2 to the x, so I'm going to write it this way. I mean, sorry, I can't write it as f because then it'd be both the same function. How about we use g, because I have not shown their inverses. I said that it appears to be, right? So if you give me the function f of x is log base 2 of x, and you give me a different function g of x, which is 2 raised to the x, it appears that those two are inverses. How could I check that they're inverses? Not the equal. How did we check that two things were inverses? What are the two things you have to show? F of g of x equals x and g of f of x equals x. You have to show that x going through both functions both ways gives you x. So I'd like to verify that now. Okay, so I'm on 6 for 6. Okay, so 6 for 6. Verify that f of x equals log base 2 of x and g of x equals 2 to the x are inverses. So here are the two things I have to show. First thing, I've said WTS in here or no? Want to show, have I done that before? Want to show? Okay, I want to show, that's what that means. It's used in math, I'm not just being really lazy, okay? We do say, you know, WTS a lot. We not WTF, although we do say that sometimes in math too. Yeah. I saw some guy at Home Depot the other day who had, I don't know what it was again, but it was like something Tango. What are the military? Whiskey, Tango, Foxtrot. Yeah. I was like, Whiskey, Tango. Oh, I get it. Okay. All right. So I want to show what? F of g of x equals x. That's the first thing I want to show. The second thing I want to show is that when you go the other way around, you get x. Am I out of time? No. 12:40. Oh my gosh, man. We got plenty of time still. Y'all hanging in there? No? Let's do one. We're going to start with f. Inside of it, we're plugging in g, right? We've done this many times now. That means inside of f, I'm putting what function? What's our g? 2 to the x. And be careful the way you say 2 to the x. You say that 2 to the x. You don't say that 2x. 2x would mean 2 times x. So just be careful with your language there. So I'm plugging 2 to the x, or 2 raised to the x, into the f function. So that means, what's my f function? It's this log one, right? So I'm going to replace this x in my log with this x right here with what? 2 to the x, right? So it becomes log base 2 of what? 2 to the x. Well, what the heck is that? Think about what the logarithm is asking you again. It's saying, what do you raise 2 to in order to get 2 to the x? X, right? What do I raise 2 to? 2 to, I should have used 3 instead of 2. 2 to, what do I raise 2 to in order to get 2 to the x? Just x. Check it with the loop. 2 to the x equals 2 to the x. Hey. Right? Yes, it works for all logs. Well, if you have log base 4, the inverse of that function is 4 to the x. Log base 10, the inverse of that is 10 to the x. So the base is going to dictate which one it's the inverse of. Okay, let's go the other way. let's start with G, and then inside F. So G, and then inside goes log base 2 of X, right? Now this one's a little trickier, because I'm supposed to take this thing and plug it in for X into G. And G is right here. So I'm actually going to take this big ugly log thing, right? And I'm going to put it right here, up there in the exponent on 2. So it's going to look like this. 2 to the log base 2 of X. Wow. That doesn't look right. I don't know what to do with that. How is that going to turn into X? Well, let me ask you to do something real quick. Take a look at that. Is everyone okay with that up to this point, that I just plugged this into the G function, which means it's 2 to whatever the heck that was? You okay with that? I'd like for you to go back in your notes and look at, not that far, sorry. This right here, when we were doing exponential to log notation. Exponential to log, right? Exponential to log. I would like for you to try and do that on this, okay? Exponential to log. So what would I write down? Log base what? 2, because that's my base. By the way, hold on a second. We need to call this something. Let's call this, just for the sake of doing it, let's call this y, okay? That way we can do it. So I'm writing this as log base 2, right? That comes from here. What goes here? Y equals what? Log base 2 of X. I know that that looks really weird, but check it with the loop real quick. 2 to the log base 2 of X equals Y. Is that what we had written up here? 2 to the log base 2 of X equals Y. 2 to the log base 2 of X equals Y. So that's what we had. Now I know, I realize this is a little confusing, but look at this. If I'm saying log base 2 of Y equals log base 2 of X, what do you think these two have to be? The same. So X must be equal to Y, right? Which means my answer up here is X, because X is Y. So this one's a little more troublesome, and I'm not going to ask you to verify that on the test. This one was pretty clean. This one a little more challenging. But it works both ways. And so the conclusion we have is that if you have a log function with a certain base, it is the inverse of that same exponential function with that base. Yes? If you're ever going to convert from one form to the other, you should do that. Okay. Now, let's see what else we want to talk about. Let's talk about going back to this here, 647. I'll let y'all go early today. Don't worry. About three or 4 seconds early. No. Graphs of log functions. Okay, what about the graphs of log functions? Well, we know already that when we draw it, we said the x had to be bigger than 0, right? Like we couldn't plug in negative values, right, for x. So I already know there's no picture to my log function over here. There doesn't exist. What else is true? Well, if I plug in 1 into any log, what happens? Careful. A to what power is 1? A to what power is 1? 0. So when I plug in 1, I get 0, right? So when I plug in 1, I should get 0. That point should always be on my graph. the point 1, 0. Go back to last class. We had exponential functions, right? What point was always on the exponential function? 0, 1, right? Whether it went that way or the other way, that point was always there. And since they're inverse functions, that flipped over should always be on the log. So it's there. All right? Now, if you go back and you look at the table that we just did, this one right here, when we plug in 1, we get 0. When we plug in 2, it's 1. 4, it's 2. 8, it's 3. 16, it's 4, right? What's happening is we go out to the right, it's getting bigger. But what happened as we got closer to 0? Half, we went down to negative 1. Get closer to 0. 1/4, you're down to negative 2. 1/8, you're down to negative 3. So here's what's happening with logarithms. As I move to the right, they get bigger, but not very fast. When I move to the left, but I cannot touch the y-axis, okay, because you can't plug in 0. What happens is it starts to dive down, and you have a vertical asymptote. This is what log functions look like if the a you have is bigger than 1. I'll refer you back to your notes. Remember we had 2 cases with exponentials? Exponential growth was if a was bigger than 1. Exponential decay was if a was between 0 and 1. We have the same sort of thing happening with logs. That's what a logarithm looks like if the a is bigger than 1. Also put down here vertical asymptote. Put here the domain. What's the domain? 0 to infinity. What's the range? Negative infinity to infinity. So look, the graph exists to the right of 0. That's why its domain is 0 to infinity. If I look at the y values, this keeps going down forever. So I've got y values all the way down. This grows to the right, slowly, but it grows. So I have y values all the way up. So my domain and my range are these two. And if you look back at exponential functions, what was the domain here? Everything. What was the range? From 0 up. So the domain and ranges have switched places, haven't they? For logs. Okay, so everything is connected. All right, both these functions are connected together. Now, if you make the a negative number, I'll do this one in red so you can see it. If a is between 0 and 1, the only difference you have is that your graph, you still have vertical asymptote, but it does this instead. All right. So there's a lot of things that changed, right? Exponential function, you had horizontal asymptote. Logarithmic function, you have verticals. It's reflecting it actually. It is a reflection over what we call the identity, which means that if you take the graph, you draw the identity function, which is the function y equals x. It's called the identity. If you take an exponential function and you graph it like this, then the log function graphed together would be a reflection over this dotted line. So if you just come over here and you tilt your head like that and reflect it, it's perfect reflection. All inverse functions have that property, that they are reflections over the identity. Okay. No. If a was -1, it would look like this. Or no, between 0 and 1, can't be negative. Well, if a was between 0 and 1, first of all, the exponential function would look like this instead, right? That would be our exponential function. Nope, it would still be this. The log function would look like, try and do this right. There. You see it? So if you still tilt your head, it's a reflection. I could have the computer graph them to convince you, but that's okay? All right. All right, so do you all remember that there were two special exponential functions? What were the two special exponential functions? 10 to the x and e to the x, right? Well, there are two special log functions. They are, first of all, log base f of x equals log base 10 of x. And why did we say that the base 10 was an important function? Base 10 number system, right? 10 fingers. That's, I mean, it's a lot of things are base 10. Metric system is base 10. And then the other one was f of x equals, what was the base for the other one? E, log base e of x. And this one is called the natural log. The natural log. But keep in mind, there are infinitely many log functions, because there's infinitely many bases you could use. Right? You could use 10, you could use 11, 12, you could use 12.6, you could use 12.6.52. Doesn't matter, right? But these are the two very special ones that are used a lot. They're used so much, so much, that there's a special notation for them. All right? Here's the special notation. If you want to do this log function, no need to write the 10. Just write log x. And then it's understood that it's a 10. It's kind of like, remember with the square root? If I put, if I put that, that means square root of 8. But if I put this out here, then you know I meant cube root. Well, if I don't put anything, it's square. Well, if I write a log and I don't put the base down there, you have to remember it's 10. All right? Y'all okay with that? Now, the other one, there's a special notation for this one also. But we can't use this because we just, So what we do is we write this. That's right. It's French, Logarithm naturel or something like that. They say it backwards or whatever. So this is not IN, this is LN. You should have both keys. Most calculators have both keys on their calculator or on there. You should have an LOG key. You should also have an LN key. And if you have an advanced calculator, you probably only have one of those, because it turns out that you only need one. But that'll be next class. We'll talk about why you only need one log. All right? Now, let me give you a little bit of historical perspective here, because there's something that gets lost here. I said that logarithms, students have trouble with them because the notation's weird. It's foreign to them. They reject it. And then we spend this time doing this loop thing, and we start really trying to get our heads around log, and then all of a sudden I change the notation on you, and I tell you there's two special logs, and the base isn't there, so you lose that idea of the loop, because you don't see the base. And I hate that about logs, because if the base is there, it keeps everything in order. So the question is, why do we write these? Like, why did we need a shorthand? What's the big deal with just writing a 10 or just writing an E? And it actually turns out, at least the story that I've heard, is there's a historical perspective on this. back when, in that age, kind of when the typewriter was a big deal, and people were writing like a lot of research papers, you know, in physics and chemistry and biology, the natural log and the log base 10 functions would be used throughout the paper. So let's say I'm writing like a book, right? I'm writing a book, or I'm writing a dissertation or research or something. I've got this 100-page document where maybe I need to write log base 10, I don't know, 400 times, 500 times in the paper. Then if I'm using a typewriter, okay, anyone ever have to subscript on a typewriter? You type, and then you have to roll the drum, and then you type 10, and then you roll the drum back, and then you type, right? So even now on a word processor, unless you're really good at them, it's still hard to subscript, right? Unless you have like a shortcut key to subscript. So it's not that easy. So what this is the story I've heard, all right? I haven't really researched this too much, but I like the story enough that that's what I'm going with. Is that if I need to write log base 10, if we all agree that I just write log x, I don't have to stop typing, right? I just write. I just keep typing away. I don't know subscripting. Same with this. I just write ln x and just keep on going. So it was a thing to speed things up. The drawback is that you as a student have to remember what they mean. Log is log base 10. Natural log is log base e. Got it? Okay. Trying to think of where I want to go with this. Seems like time's going really slow today. 6, I know. Or am I at 9? Yeah. I don't know. No, next week? Oh, I don't have it on this. Sorry. I think it's Tuesday. Oh, I don't know when it is.
Oh, dude.
20 what? 23rd. So we got a little ways to go. All right. How to sketch a log function. All right. Look, different teachers teach this different ways. All right. How to sketch a log function. I already showed you how to sketch log base 2. Right? Didn't we do that a little while ago? But we had to be kind of clever. Like we plugged in 1, and then we plugged in 2, then we plugged in 4, and then 8, and then 16. And we had to kind of think through that, didn't we? But that's not the way that I recommend you sketch a log function. Here's the way I think you should do it. And I'm going to do it with an example. Please remember, this is kind of the technique I want you to use. I want us to sketch f of x equals ln x. I want us to sketch the natural log. Now, what I could do, right? What I could do is try and make up a table, couldn't I? Please don't write this down. But I would have to come up with numbers that I know would work over here, right? Like with log base 2, it was what? 1, and then 2, and then 4, and then 8, and then 16. But what would I use here? You know what I'm saying? Like this is base e. So what do I use? So here's the way I would recommend you do this instead. We know that this is the inverse of what? This function is the inverse of which function? The inverse of that function is just e to the x, isn't it? Isn't it? Yeah, this you can write down. And what do we know about inverse functions? They switch x and y coordinates. So couldn't you make a t-table based on this and then just switch the x and y coordinates? And that would be the coordinates of your red one? That's the way I would recommend you do it. So what I'll do is I'm going to make a t-table based on x e to the x, do the standard -2, -3, -2, -1, 0, 1, 2, 3, and then plug those into your calculator and figure out what they are. whatever those answers are, we're going to flip them over, and that's what we'll plot. So do we know these? We did this last class, didn't we? We have these values. 0.049, then what's the next one? 1353, 0.367, 2.718, then did we go further? 0.86. Okay, so refer to last class. Is that like a video game? Oh, but is that like a video game song? Oh, okay. All right. All right. Do you get what I'm doing here? I'm using the inverse in order to graph this easier. I look at the inverse of natural log of x, which is e to the x. Why is this e to the x the inverse of this? Because what's the base of natural log? E. Okay, you had to know that because I told you. And so then you make a regular t-table off of that. And now what I can say is that for this function, right, if I made a t-table, x, natural log x, it would be every one of these coordinates flipped. So it would be 0.049, negative 3, 0.1353, negative 2, 0.367, negative 1, 1, 0, 2.718, 1, 7.389, 2, and then 20.086, 3. And those are like x and y coordinates. So you go plot those. And I think I can probably squeeze one in right here. Watch the way I'm going to graph this. Notice I'm not drawing the left side of the graph. Why? Because the domain restriction on logs, right? I don't need that left side. The biggest x value I have is 20. So I'm going to put 20 out here. That means this is 10, 5, and it sounds like they're having fun out there. We're in here doing this. 1, 2, 3, negative 1, negative 2, negative 3. That will be pretty standard, right? And now it's just a matter of figuring out where these things are. My x-coordinate is 0.049. That's just barely to the right. Barely, and then down 3. So like, I don't know, somewhere in here. And then just a little bit further to the right, down 2. A little bit further to the right, down 1. Then 1, 0. 2.718, 1. So we're just, look, we're kind of ballparking this. We're not getting this exact. 7.3892. So 7.389, somewhere around here, up 2. So somewhere around there. And then 20 point something 3, which is way out here. And then you can connect them together with a nice smooth curve. Remember, you've got your vertical asymptote there. You get the idea? All right. So let me see if there's stuff that you can look at for homework. And then I'll let you go. We'll do a quiz grade right now, okay? So what I just need you to do is just take out a sheet of paper and put your name on it, all right? And then just turn that in. Yeah, but it'll be faster if you just all do your own. Page 446. Let's go 9. through, no, this is just homework. Odds. So those problems involve converting from log form to exponential or exponential to log, just rewriting. And then numbers 25 through 35 odd. I realize I could have said 9 through 35 odd, but I'm separating them because they're two different concepts. On these, they give you a problem something like all they write is log base 864. And they want to know what that is. So what you could do is you could call it, let's say, x, and then write your loop. 8 to the x is 64. And then you're actually doing exactly what your homework that I gave you right before this is, which is you get both sides to look like the same power, like 8 squared, and then you match up the tops, and it's x is 2. All right, so you have to go from log form to exponential form first, then you just do what we did in the previous section. Okay, make sure you put your sign in, your name on the sheet, put that on that corner of the desk. Have a good weekend.